Greetings, everyone. The title of today's lecture is Languages and Semantics. We have a pretty simple agenda today here. We're going to define completely the syntax, the semantics, and an evaluator for a very simple language. A language in which we only have four expressions, x, y, z, and w, which we think of as variable expressions. The idea is we're going to talk about how to assign semantics to such expressions by defining functions that take expressions x, y, z, or w as arguments and that return values in some domain of discourse as results, where those results might be, for example, natural numbers or maybe Boolean values. At the end of the lecture, we're going to cover some more advanced coding topics in Lean, but they're important topics in logic in general because they allow you to write logic in a concise and expressive way. And those are the concepts of parametric polymorphism and type inference. So we'll get to those in a bit. For now, what I'd like you to do is pause the video, crank up your VS Code environment, open a new file, and save it in your source Scratch directory. And you might as well call it languages_and_expressions.lean. So pause now, open and save that file within the source Scratch directory. It has to end with the file name has to end with .lean, or else VS Code won't recognize it as a Lean file. So that's all you have to do. So pop over into VS Code, crank up, pause the video, and come on back when you're ready to go. Good. Okay, so here we are back over in our Lean editor in VS Code. As you can see, I've created a file within my Scratch directory called languagesandevaluation.lean. That's here. I have the file, it's empty, open here, and my Lean info view and messages panel over here. I'm going to close out this project browser so that we have more room to work on the screen. And I do that with Control B on my Windows machine. For you, it would be Command B. There are other ways of doing it, but that's the shortcut way of doing it and the quickest way to do it. So now let me make sure that the text on my machine is big enough that you should be able to read it on your screen. Give me some feedback if text is too small for you to read on your screen. It should be okay if you use a full screen presentation mode. Okay, so here we go. So the idea here is that, and that you've seen before, is that the syntax of a language is a set of symbolic terms, all of the terms that can be formed in one way or another in a given language. So think of the syntax of a language as defining a set of sentences or terms or expressions, if you want to call them expressions, in a given language. This is a notion of a formal language in computer science. It's really a set of strings, is the way that you'll think about a language in your theory of computation class, that's coming down the road. The semantics of a given language assigns a meaning in some domain of discourse to each term or expression or sentence or string in your language. And an evaluator for a language takes a term, an expression in a language, and an interpretation potentially for variables in such terms, and returns the corresponding meaning or value of that expression. So think about an evaluator for a Python program, right? It takes a Python program as an input and returns the meaning of that program as an output, which is the result that it computes. Okay, so an evaluator evaluates expressions in a given language, reduces them to what they mean, and returns that meaning as the result of the evaluation process. So we're going to see in this lecture how we can formally define the syntax, semantics, and an evaluation function for a very simple language. And the language that we're going to build here in this lecture is a language with just four terms. Those terms are going to be called X, Y, Z, and W. And you can think of them as representing variables in a Python program or variables in some other, in C++ or some other language that you're familiar with. Okay, so how are we going to define the semantics of such a language? Well, we have our syntactic terms X, Y, Z, and W, and we want to map each of those terms to a corresponding, let's say, natural number value. Okay, we'll take the natural numbers as our domain, our semantic domain, and now we want to define an association or mapping from the variables x, y, z, and w to corresponding natural number values. So maybe, for example, x could mean 0, y could mean 0, z could mean 0, and w could mean 0. That would be one interpretation. If x means 1, y means 0, z means 0, and w means 0. That's a different interpretation. If x means 1 and y means 2 and z means 3 and w means 4, that's yet a different interpretation for that same set of symbolic terms, for that same set of expressions. Okay, so the key insight here, ready, is we can define interpretations as functions. Okay, so a function takes a value of a term, takes a term in a language, and returns its corresponding meaning. So we need a function, for example, that takes any one of our 4 terms, x, y, z, or w, as an argument, and then returns its corresponding natural number value as a result, and that function then represents one possible interpretation for our language. Okay? Different functions then would be used to represent different interpretations of that same set of 4 syntactic expressions. Okay, so now given an interpretation function to determine the meaning of a given expression, you just apply that function to the expression and you get back the resulting value. Now finally, we can define an evaluation function, and an evaluation function takes a term and an interpretation function and returns the meaning of that term given that interpretation function. Okay, so if the terms are x, y, z, and w, eval will take our evaluation function, we'll call it maybe eval, will take a term like x, and it will take an interpretation, one of these functions, that maps terms to corresponding values, and it will compute the corresponding value by applying the function, the interpretation function, to the term and returning the result. Okay, so that's what we're going to do. And we're going to start by defining the syntax of our language. And we've already seen that we can define the syntax of a language of simple expressions as an inductive data type. So the values of the type will represent the terms in the language. So consider a simple language, the simple language we've already talked about, with just 4, we'll call them variable symbols, x, y, z, and w. That's it. Those are the only terms in our language. So we can formally, and when we use that term formally, we mean with mathematical precision, we can formally define the syntax of this language as a very simple inductive data type. So let's do it. Let's define an inductive type. We use the keyword inductive. The type name comes next. We'll call our type var, short for variable. And variable will be var will be a type, okay? And the values of that type we'll just enumerate here. So this will be kind of an enumerate, what we'd call an enumerated type, where the term, the constructor x, all by itself, is a term of type var, okay? Now, putting the :var in is optional, but I like to do it anyway because it reminds me and makes it clear that x is a term or a value of the var type in the language. And we just now need to do that for the remaining terms in our language. So you go ahead, take a second, fill in the rest of this inductive data type definition, and then I'll complete it. Okay, so y is also a term of type var. Capital Z is a term of type var. This is a variable name completion that you're seeing in VS Code. It can be very helpful. It can also be annoying. So W is of type var. If I hit the escape key here, it stops trying to figure out what I want to type. Good, that's it. That's our language definition. That's the syntax of our language. Okay, so we can now explore what we've done a little bit. So question, what's the type of var? Well, it says it right here. Var is of type with a capital T. So big T type is the type of all computational data types. So var you think of as a type. It's like string or bool or nat. It's yet another type. It's a a type we've defined rather than a type definition we've inherited from some library, but it's a new data type. Okay, so if we check the type of var, then Lean will tell us over here in our messages window that the type of var is type. Question: what's the type of X? Well, unknown identifier. The constructors of a type, like X, Y, Z, and W here, are defined in a namespace with the same name as that type. So to refer to the values within a type definition, to refer to the constructor names within a type definition, we need to refer to them as in that particular namespace. So we have to say var.x here. And of course, var.x is of type var. Okay, so x is a variable. Okay. If we don't want to have to prefix all of the constructor names with var dot, and if it doesn't cause any ambiguity or name clashes with anything else in our code, then we can open the var namespace like that. Okay, and from that point forward, you can then omit the namespace name in front of the identifier x. So we can now just check to see what x is, and we're told that, well, x is a value of type var. So make sure you understand that x is a value of type var. You have to wrap your head around the notion of types, and types as defining sets of values, and values being of the types that define them. So here, x is a value of type var. Var is a value of type because it represents a type. And if you're really curious, go off and figure out what the type of type is, and you might be amazed. But we're not going to go down that little rat hole right at the moment. You can if you want. Okay, so we are good now. We have opened the var namespace, so we can refer to x, y, z, and w without having to type var dot in front of those constructor names. Okay, so question. What is going to happen if we use Lean's eval command to evaluate x? I'm not going to type the x here yet. Well, we've called x a value of type var, but we could have given it any name. We're just thinking of it as representing a variable in some language, and we'll make that idea make more sense later on. But for now, really, x is just a literal expression of type var. So here, this x is a literal expression of type var. Now, what happens when we evaluate a literal expression? We just get the value that it immediately represents. So if we evaluate x, well, we get this funny thing here, #0. That's because the eval command kind of forgets the names of constructors. Let's see what we get if we eval y. Oh, #1. What do you want to bet that if we eval z, we get #2? Indeed we do, and you can be assured that if we eval w, we get #3. The evaluator of Lean expressions that we're using here kind of forgets constructor names and just replaces them with these pound numbers. So if you see that, you might want to use the reduce evaluator instead. As I said in an earlier lecture, Lean builds in two evaluators, one that's kind of really fast and one that's kind of more helpful. So if we reduce the term x, the literal expression x, we just get the value x, which you can think of as this value right here. Okay, so in particular, x is not bound to any of our values at the moment. We have only defined the syntax of our language at this point. We haven't defined an interpretation of what x means in the language that we are defining. Okay, so let's go ahead now and do that. So I'm going to put a label here. We're now going to define the semantics of our language. Okay, and you know, you might want to take all of this stuff here and delete it or put it in a comment. It's not really an essential part of what we're doing. We just put it in to kind of explore the meaning of what we've done. So for now, look at how simple this is. It's very, very easy. We define the syntax of a language as a set of terms. And in this case, we've defined the set of terms by just enumerating them one after another. There's no circularity here. There's no fancy, you know, constructor takes value of the same type that we're defining. It's just a set of terms, X, Y, Z, and W. How many terms are in our language? 4. That's it. Okay, very simple. So now semantics. Remember that a semantics associates a meaning with each term in a language. So we have 4 terms in our language, X, Y, Z, and W. We first need to say, what is the domain of meanings to which our symbols will be associated? And let's just pick as a domain of discourse here, the domain of natural numbers represented by values of type nat. Okay, I said that carefully. We're going to let the semantic domain of the language we're defining be the natural numbers. That's a mathematical concept, but we need a representation of those to use in our language, in our definition here, so we'll select the type nat. Remember, that's a unary representation of the natural numbers. So let me say it again. We're going to define the semantic domain of our little language to be the natural numbers as represented by values of type nat. Okay? And so in particular, what we're going to do is we're going to associate with each of our 4 syntactic terms a corresponding value of type nat. Okay? So as an example, under one interpretation, we might associate each of the 4 symbols with the natural number with the nat 0. Okay? So we need a way to say what each what natural number each of our symbolic expressions means. And we're going to do that by defining a function that takes as an argument one of the syntactic terms, X, Y, Z, or W, a value of type var, in other words, and that returns the natural number that we interpret that variable object as meaning. Okay, so as a first example, well, let's actually be a little bit clear. We're going to let's define a type. Let's define a type called interp underscore nat, and this is going to be a type of function. Okay, it's going to be a function that takes a variable, a var object like X or Y or Z or W, and returns a natural number. So what does this definition mean? This is a little bit confusing. We're binding the name interpnat to a type, and the type is var to nat. Okay. So in other words, we're just giving a short name, interpnat, to this type. Okay? So I'm saying that any function of this type, any function that takes any value of type var, either X or Y or Z or W, and that returns a nat, any function of this type we can think of as being a function of this type as well, interpnat. It's just a shorthand for this. Okay, that's all that we're doing. It's a variable expression in the lingo we've developed up until now. Interpnat is a variable expression that reduces to this value, which is a type value, the type of function that takes a variable and returns a natural number. Okay, so let's give some examples of functions of this type. So let's define, for example, an interpretation under which each of the variables is interpreted as having the value 0. So let's call our interpretation function interp underscore 0. Okay, it's going to be a function, and it's going to be a function that takes any var object and returns a nat. So that's the type of the function. Okay, and given that this type is also called interpnet, we could replace this with interpnet and it means the same thing. Okay. For now, I'll just leave it as var_nat so that it's absolutely clear what's going on here. So we're defining a function. Here's the name of the function, colon. Here's the type of the function. And now we're going to define the function by cases. So the idea is the function takes an object of type var and returns a value of type nat. Now, what are the possible values of type var? What are the different cases? Well, each case, there's 4 cases, right? The argument of type var could either be x, or y, or z, or w. Those are the only 4 values of type var. And if we assign, associate a return value with each of a natural number with each of those symbols, then we have our interpretation. So let's associate the semantic value 0 with x, and let's do the same thing for y, z, and w. Okay, can you go ahead and do it? Just put in the 4 additional cases here. Something weird is going on. Something weird is going on. I want you to pay attention to this. It's one of these failure modes that once you recognize what's going on, it'll be easy, but it can be extremely confusing if you don't see what's going on. We have an error here that says the equation compiler error. Equation 2, that's this equation, has not been used in the compilation. Note that the left-hand side of equation 1 is a variable. Yeah, okay, so look, here's the rule of thumb. From now on, whenever you use a constructor name in defining a case in a function, go ahead and please do add the namespace name before it, even though we've opened the var namespace. When you're writing these so-called pattern matching rules, where you're matching up the value of a parameter with one of its possible forms, go ahead, please, and make the namespace explicit. So here's the idea. If the argument to this function is var.x, then we return 0. If the argument to this function is var.y, then we'll return 0. Now we have an error. And what does it say? Well, it says non-exhaustive match. The following cases are not given. The following cases are missing because we haven't yet given values for var.z and var.w. And one of the interesting things about Lean is that it insists that all functions are total, which means that they have to return a value for every possible value of each of their arguments. So we need to include the cases. You go ahead and finish it off. Right, var.z colon equals 0, and finally var.w colon equals 0, and there we go. So there's an interpretation for our variables, an interpretation under which the meaning that we associate with each of the variables is the natural number 0. That's it. Okay, now we can obtain, listen carefully to how I say this and learn how to say this. We can obtain the value of any syntactic term in our language under this interpretation by applying this interpretation function to that term. Okay, so let's see how that works. What do we get if we evaluate the application of interp 0 to x? Let's see. I see what happened. Okay, so I'm sorry. I commented out this one important piece of stuff here. I wanted to open that namespace. And so, in fact, we now can go ahead without the var dot here. Okay, so that's what's going on. Sorry about that. Okay, you can go back and think about that again. I'm not going to remake the video, but be aware that that's why I ended up having to type the namespace names here. It's still not a bad idea to go ahead and prefix the constructor names with their namespace name for clarity, but in this case, this probably is sufficiently clear. So now, if we apply this interpretation function, interp0, to the argument of type var, namely x, here's what happens. This is what kind of expression? This is an application expression in which this function is applied to this value. So what do? We look up the definition of this function, and the definition is by cases. The argument is x, and so we look at each case, and we do matching. If the argument x matches this case on the left-hand side of the colon equal, then the return result is 0. And that's what happens here. If we interpret the term y under this same interpretation, we also, of course, get the value 0. And the way that works is that this function application expression is evaluated. Go back and look at the previous lecture if you're not clear about that. Okay. We evaluate the function application expression where we apply this function to this argument, y. How does that work? Well, we look up the value of this identifier, interp0. It's the value of this function is given by cases. We look at the argument y. Does it match the first case? No. Does it match the second case? Yes. So the function application expression reduces to the value on the right side of this expression. That's a literal expression, 0, so you further reduce it, you get the value 0, and the result of this function application expression then is 0. And you can see, and go ahead for yourself, make sure that both z and w also evaluate to 0, as you expect. And in fact, they all do. Okay. Here's a little aside in Lean. We have a case here or a situation here really where for any value of type var, we want to return the same value 0. There's a more advanced form of pattern matching in Lean that uses an underscore to match any argument value. So here I've copied and pasted the initial function definition. I've attached a tick mark to the name so we don't have conflicting names. Remember, we can't bind a new value to a name that's already bound. So I changed the name of my function. And now, instead of typing all of this, I can say, no matter what value you see for the first argument to this function, go ahead and return 0. Okay, so it's the same interpretation function, but it's written in a more convenient form. This underscore is called a wildcard, and that's a term that's used throughout programming languages and software engineering and string pattern matching and so on and so forth. It's a pattern that represents any value of some kind. So now if we apply this new function definition to the same arguments x, y, z, and w, we get 0, 0, 0, 0, just as you'd expect. Okay. Okay. Now, what I'd like you to do, and you can pause the video here for a second, and then I'll come back and complete the assignment for you, is I'd like you to define an interpretation function. Let's call it interp _1 _2. So instead of a 0 here, we'll do _1 _2. And this definition should associate the value 1 with x, the value 2 with y, And for z and w, both are associated with or have as their meaning the value 0. So x is 1, y is 2, z and w are both 0. And use pattern matching, use a wildcard to take care of the later cases. Go ahead and pause your video and finish off the definition. Okay, all right, so here we are. So so the way that this function is going to work is when interp12 is applied to an argument var, it's going to return a result, well, as defined by the following cases. If the argument of type var is x, then we'll return 1. We have an error here because we haven't defined values for all of the cases. Okay, but we're about to do that. If the argument is y, then we'll return 2. And if the argument is z or w, we could write those out explicitly, but we can also use a wildcard here, then we'll return 0. And you see now that this function is defined for all 4 cases, even though we've only used 3 lines of pattern matching code in our definition. Okay, and now sure enough, let's just cut and paste this, and we'll change the function name here. We'll change I am copying and pasting _1 _2 here, 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 and here. And you see that under this interpretation, interp12, x has the value 1, y has the value 2, z and w have the value 0. Once again, my phone is ringing during the middle of class, and it's a spam call, and I am not going to answer it, and we're back. Okay, so this is actually really cool because now we have 2 distinct interpretations for the same set of syntactic terms. Under one interpretation, x, y, z, and w all have the meaning 0. Under this second interpretation, x means 1, y means 2, and z and w both mean 0. Okay, so we've defined 2 different interpretations here for the same set of syntactic terms. Okay, so as an exercise in your homework, I'll have you define an interpretation under which x means 1, y means 2, z means 3, and w means 4. And where you'll use the eval command to show that your definition works as expected. Okay, so it's easy, as you can imagine. This is a 1-star exercise. Okay, so what's the takeaway message here so far? We define the syntax of a language as an inductive data type whose values are expressions, terms in our language. Okay? For the language here, our syntax has only 4 terms, which we've enumerated and called x, y, z, and w. Those are the constructors of the inductive data type. And because they don't take any arguments, they're just, parameter free. There's 4 of them. There's only 4 terms in our language. That's all there is. We can then define an interpretation that maps those terms to corresponding meanings by writing 1 or more functions. An interpretation function, a function that takes a term in the syntax of our language and returns an associated value in the domain of discourse. Here, the domain of discourse so far has been the domain of natural numbers as represented by values in leen of type nat. Okay. Of course, nothing prevents us really from choosing a different domain of interpretation. Right? So we decided that we would interpret our variables as having natural number values, but we could just as well have decided that we would associate our variables x, y, z, and w with values of with Boolean values as represented by values of type bool in leen. The values of type bool in leen are called TT and FF. Those are the only 2 values, and they represent the Boolean values true and false, which you should be familiar with from your other programming classes. Okay, so if we want to think about the type of a Boolean interpretation, it's not interp nat, but we could call that type interp bool, and here we replace nat with bool. Okay. So the type of function from var to bool, well, that's it right there. That's how you write that function type. Okay, so if we define functions that take any value of type var and return a corresponding Boolean value, then we have a Boolean interpretation rather than a natural number interpretation of terms in our language. Okay? So we've separated the concept of syntax from the concept of semantics. The syntax is just given by a set of syntactic terms that don't have any inherent meaning, x, y, z, and w. We give those terms semantic meaning by defining various interpretation functions. So if you would kindly, let me turn down my phone so that doesn't happen a third time. So if you would kindly go ahead and pause the video and take a minute to write an interpretation function, let's call it interp_ff, that associates a semantic meaning false with each of our 4 variables. And remember, false is represented in leen, the bool type by ff. So pause the video and then come back and we'll do it together. Okay, we're back. Okay, so let's define a Boolean interpretation that associates the Boolean value false with each of our variables. We'll call it interp_ff, as I indicated. And what's the type of this function? Yes, indeed, var to bool. Or we could write it as interp bool. Okay, whoops. Okay, and I actually prefer just to keep it like this so that it's clear. So you don't have to decode an additional symbol to understand what your program's doing. Okay, so given any value, any syntactic term, any value of type var, we want to return false. So we can use a wildcard here, and I hope you saw that when you did the work. And for any value of type var, we will reduce that expression to the Boolean value ff. Okay, so we can now interpret. I'm going to reuse some of this text by cutting and pasting this and replace _1 _2 with _ff. And look at the interpretations of x, y, z, and w under the interpretation interp_ff. And as expected, x under this interpretation means false, y under this interpretation means false, and so for z and w, all of them mean false. So suppose now we wanted a different interpretation under which x is true and y, z, and w are false. Actually, let's do a little slightly more clever case where x is true and w is true, y and z are false. And we'll make a little mistake along the way and see how not to make that mistake in the future. So I'll call this interp tt ff tt. Okay, so those will be the interpretations of x, y, z, and w, respectively. This function takes an object of type var as an argument and returns a value of type bool as a result. And here's what we can do. If the argument is x, we'll return tt. That's true. We have an error in our definition, which is that we haven't defined all the cases yet. And now we'll try something clever that won't turn out to work. We'll say, well, for anything else, we'll return false unless it is w, in which case we'll return tt. Okay. And now we have an error here. And once again, it says equation 3, that's this equation here, this pattern matching equation, has not been used in the compilation. So this tells you leen is ignoring this line of code in your function definition. And why do you think that is? That's right, because this underscore matched y, z, and w, and so gave values for w in particular. So we can't really use pattern matching here. We need to say if this is y, then it's false. If this is z, then it's false. And if it's w, then it's true. Okay, so there's an interpretation under which x, y, z, and w have different values than they do under the FF interpretation. So here I'll use cut and paste again to replace the name of the function. Okay, so under this new interpretation, x means or has the semantics of meaning true, y false, z false, and w true. Okay. Good. Okay, so you should be feeling comfortable now about how to define, simple functions by case analysis more generally. Okay, so an exercise for you to do at home. It'll be part of the homework. We've seen that we can define at least two different interpretations of Boolean interpretations of four variables. How many possible interpretations are there of four variables? And a good way to think about this is to start with, let's start with one variable. How many Boolean interpretations are there for one variable? How many ways are there to associate a single variable x with a Boolean value? Well, there's two, right? You could interpret x as meaning true, or you could interpret x as meaning false. Now suppose that you have just two Boolean variables. Now how many interpretations are there? Well, when x is true, how many possibilities are there for y? And when x is false, how many possibilities are there for y? So how many total possibilities are there when you have two Boolean variables? Now consider the case of three Boolean variables. When z is false, you've got all the preceding possibilities for x and y. And when z is true, you've also got all of the preceding possibilities for x and y. So how many possible interpretations are there? And now with four variables, how many possible interpretations are there? Are you seeing maybe what the general formula is for the number of interpretations of n Boolean variables? What about when there are 10 Boolean variables, Boolean valued variables? How many different interpretations are there? How about when there's 100? As an exercise, I'm going to ask you to actually do a little bit of busy work and write down all possible interpretations as functions for the four Boolean variables in our little language here. Okay, good. And there are some other exercises that I'm going to ask you to do. Okay, cool. So look, we have made a lot of progress here. We have a syntax for our language. We have 1, 2, actually that's equivalent to the first, 2 different natural number interpretations for our language. And we have a couple of Boolean interpretations for our language, 2 of them. So we have one syntax for which we have multiple different interpretations. Several of our interpretations take nat as the semantic domain. Several of our interpretations take bool as the semantic domain for the same set of syntactic terms. And we've seen that given a syntactic term like x and an interpretation like this one here, interp tt, we can compute automatically. So we're doing some automated reasoning here. We can compute automatically the value of that term under that interpretation by applying that interpretation represented as a function to that term. Okay, so when we apply this interpretation function to this term, we get the appropriate meaning of x under that interpretation. Under a different interpretation, x means something different. So if you go back and forth between here and here, you see that x means something different under the FF interpretation than it does under the TTFF FFTT interpretation. Okay? So the same syntactic term can have different meanings under different interpretations, even for the same domain of interpretation, here nat, or here bool actually. And in fact, we can define different domains, we can select different domains of interpretations as well. Okay, so that takes us through the concepts of syntax and semantics. And now what we want to talk about is evaluation. So an evaluation function is a function that takes a term in a language and maybe some additional information, in particular an interpretation, and that returns the meaning of that term. So we talk about evaluating a Python program. What does that mean? Actually, kind of the evaluator takes the text of the program, does some stuff, and returns you a value. That's evaluation. Okay, so evaluation. And we're going to model evaluation here also as a function. So let's look at a first example. We're going to call our first evaluator eval under nat. We can actually use those, evaluate, eval under nat. We can use these special characters like nat and others as ordinary characters in identifier names. And so this evaluator is going to take a term in our language, a value of type var, okay, and it's going to take an interpretation as well. We've seen that you can have multiple interpretations that take vars and return natural numbers, for example. And one interpretation might return 0 for all of the variables. A different interpretation might return 1 for x. So there are many different possible functions, many different possible interpretations for terms. So we want to be able to take any interpretation. So our second argument will be a function, an interpretation of type var to what? Well, yeah, var to nat, right? Okay. And now the idea is that we're going to take a term like x and an interpretation like, for example, interp 0 as arguments. So here's x, here's interp 0 or interp 0 prime, which is the same function. And we want to return a value, the value of that function under this interpretation. We want to return the value of this term under this interpretation. We know we can do that by applying a function to a term, and we're going to get a value of type nat at the end of the day. Okay? So we're going to evaluate a variable under a given interpretation and get the value of that variable under that interpretation. So how's this going to work? Well, we're going to see a slightly more sophisticated form of pattern matching here. Okay, and I'm going to explain what's going on. We need to give, we need to ask, we could do this in the following way. We could say, well, if we get x as a first argument and then some arbitrary interpretation, we need to give a name to this argument so that we can use it. So we're actually going to do something different here. We're going to give names to the arguments to this function. So we're going to call the variable that we get v only for purposes of evaluating this function. Okay? So the variable v is going to be temporarily bound to the value of this argument. We need to give a name to this argument as well. This argument is an interpretation, so let's give it the name I. Good. So now we have an argument named v bound to an argument of type var. We have an argument named I bound to a value of type var to nat. In other words, I is now bound to this function. And to compute and return this natural number, what expression should we put right here? Remember, to evaluate, to obtain the meaning of a term under an interpretation, where that interpretation is represented by a function, what do? We apply the function to the term, apply the interpretation function to the term, to get the corresponding value of that term. So we need to apply the function I to the term v, and that's it. That rule works for all possible values of var and all possible interpretations. Okay, so the new thing that's going on here is that when we use an unused variable name, and it could be Q here, okay, it could be Fred, it can be anything other than an already used variable name. Okay, we can't use X here because that's already used. Well, maybe we can. No, we get an error, right? Yeah, because this is interpreted as just the value of var given by the X constructor. Okay, so good. We could, in fact, have given 4 rules that all look the same, except for, no, I'm leading us down a bad path here. Okay, as long as we use unused variable name in a pattern, it will match any value of an argument type. So no matter what value is given for the first argument to eval nat, that's matched by v. No matter what value is given for the interpretation argument, that's matched by I. So these two previously unused variables appearing in a match expression match any possible combination of argument values. And given those values, a term and an interpretation, we can reduce the term to a value by applying the interpretation function to that term. That's a lot to digest, okay? It's a very, very small amount of code, as you see, but there's a very deep concept here. So take a few minutes, pause the video, think about and make sure you really understand what's going on here, and maybe use this function a few times to see on your own to see how it works. So if we evaluate, this is the lean command eval, if we evaluate the application of this function to 2 arguments, let's say one of type var, such as x, and now what do we need to give for a second argument here? We need to give a value of this function type. In other words, we need to give an interpretation here. An interpretation that associates x with a natural number type. Well, we have some interpretations, like interp 0, for example. So let's evaluate x under the interpretation interp 0 and check it out. There we go. Okay. If we evaluate, let's copy this and use a different interpretation. If we evaluate the natural number value of x under the interpretation interp 1 under 2, why now we get a different value for x under this different interpretation. Okay, and so we've defined a general purpose evaluation function here that given any term in our language and any interpretation that gives a natural number meaning to that term, we can compute and return the value of that term under that interpretation. Cool? Okay, so that's sort of the end of the major story here. But there's a little bit more. We also have given some interpretations of our syntax with a different domain, the domain with the semantic domain of Booleans. So would our natural number evaluation function work if we tried to use it to evaluate x under a Boolean interpretation? And you can guess probably that the answer is no, and we're going to get a type error. So if we try to apply eval nat to the variable term in the syntax of our language x under interp ff, we get a type error. Okay, and here's the error message: type mismatch. At function application, eval under nat x interp ff. The term interp ff has the type var to bool, but is expected to have the type var to nat. Okay, so that's not going to work. We can't use this evaluation function with an interpretation function of type var to bool because eval underscore nat expects as its second argument a function of type var to nat. So we will comment out this broken line of code like that, and let's look at defining a different evaluation function, a Boolean evaluator. So we'll define eval under bool to be a function whose first argument is of what type? The same type. Any expression in our language, any one of x, y, z, or w. But that now takes as its second argument a Boolean interpretation function, a function of type var to bool. Okay, and that at the end of the day reduces a variable term in our language, x, y, z, or w, to a value of type bool. Okay, good. Now what's the implementation going to look like? Pause the video and see if you can finish it off, and then I'll come back and work through it with you. Okay, here we are back. Good. So eval bool is going to take any variable in our language, any expression or term in our language, let's just call that v. So this unused variable, see, the use of this variable only matters until the end of this expression. So outside of this expression, v and I are irrelevant. So we can use them again here. So the first argument we're going to call v. When eval bool is applied to two arguments, we're going to call the first one v. We're going to call the second one I. And we're going to compute the result by applying the Boolean interpretation function I to the variable argument v, and that's it. Cool. Okay, so let's see now, let's copy and paste, well, no, let's go ahead and write it out. So let's evaluate, using Lean's evaluation, what we get when we apply eval bool to the variable term in our language, in the syntax of our language, x, with a Boolean interpretation, like, for example, interp ff. And not at all surprisingly, when we evaluate x under the interpretation interp ff, we get ff. If we were to evaluate the expression x under tt that's our other interpretation, why the value of x under this second interpretation is true. Okay, good. So we've seen that we can define interpretations that associate terms with values in different domains, in this case nat and bool. We can define evaluation functions that take a term and an appropriate interpretation function, one from var to bool or from var to nat, and that then reduce a term to its value by applying an interpretation function to the term to get the corresponding value. Okay. And now the last topic for this lecture is that of polymorphism. And I want you to look at these two definitions. Val underscore nat is of type var to nat, and we've already explained how it works. Eval bool is identical, except there's a bool here and a bool here, instead of being a nat in each location. So one of the things computer scientists and good software engineers don't like very much is repeating themselves. There's a principle called don't repeat yourself, the DRY or dry principle. And one of the ways, I mean, we haven't repeated ourselves exactly because we have nats in some places, here, here, and here, and bools in other places, here, here, and here. But otherwise, we've repeated ourselves. In other words, these two definitions only vary by the type of one of the values that it deals with, nats in this case, and bools in this case. In such situations, we can avoid the repetition by using what's called parametric polymorphism. And the idea is that we abstract away the concrete types that appear in multiple definitions and turn them into a parameter. Okay, abstraction replaces a bunch of concrete elements of different kinds with one parameter. And now you can obtain the original definitions by just substituting in different values for that parameter, bool in one case or nat in another case. So here's how we would do that. We'll define eval, leaving off the underscore nat or underscore bool because we now want a definition that is polymorphic in the type of domain value that it deals with. We'll replace the concrete elements here with a parameter. So we're going to use a Greek, we don't have to do this, but this is the way that people do it. We're going to use the Greek letter alpha to represent a value of type. Okay, what are some values of type? Let me tell you, if you're not quite clear about what I'm asking here, you have to work really hard to wrap your head around this notion. We've seen the value big T type. What are some values of that type? Yeah, bool, string, nat, var, and others that we've defined along the way. Okay, so we're saying here eval is a function that takes as an argument, a parameter, a type. So one of the types that we could provide as a parameter would be bool. One of the types that we could provide as a parameter would be nat. Okay. Given such a parameter, the type of eval alpha is then var. We take any term in our language, and then we take an interpretation that maps from var to what? Well, to a value in that domain, the domain given by the type alpha. Okay, so you can see that where we had nat and bool before, we now have a type parameter, and wherever nat or bool appeared in these expressions, I thought I turned down my phone, but I didn't. Wherever the type appears previously, we replace it with alpha here. Okay, so here we now have a definition of the type of a general evaluator that takes any term in our language and an interpretation that maps terms to values of type alpha and returns a value of type alpha. And now the code is going to be, well, you figure it out. This argument is going to be implicit, so we're not going to need to list that argument. The first argument after the type argument is var. We'll call that v. We have a interpretation argument I, and I'm sorry, I will power off my phone. We take, we match up the syntactic term with the variable v. I refers to the interpretation function, and of course the result is colon equals is iv, just like that. Awesome. Okay, so there we have it. There we have a general purpose evaluator that can take interpretations of any type. Okay, so let's see how it would work. Let's eval. We need a type parameter here. So let's say nat. Then a term in our language, like x. Then, given that alpha is nat, That's the first argument here. We needed an interpretation from var to alpha, but alpha is nat, so we need an interpretation function of type var to nat, and that could be interp0, for example. And of course, we have to apply our function at the beginning. Sorry about that. So we're evaluating x given this interpretation function from var to nat. Okay. Eval, type argument, alpha, term in our language, interpretation of type var to nat, and the result. 0 is the value of x under the interpretation interp0 of type var to nat. We can evaluate the application of our general purpose eval function to a term given a Boolean interpretation by specifying bool as the first argument to eval. So we have eval, alpha is now bool, the same term x, and now we need a Boolean interpretation. What happens if we use interp0 here? Nope, type mismatch. Okay, and you should take a minute, maybe even pause the video, and read carefully through this error message to understand what it's saying. Okay, but if we give a Boolean interpretation here, like interp_ff, then it's going to work just fine. So here we evaluate the variable expression, if you will, x, under this interpretation of type var to bool. Pretty cool, right? Finally, so this is the concept of polymorphism. Here, I'll put that in this kind of comments to make it look even more important. And the final topic for today, and I know this is getting to be a lot, but spend some time watching this lecture multiple times, especially on this last little bit here, and you'll be all set to go for much of the rest of this class in terms of what you need to know about definitions in Lean. The idea here is the following. So we're going to talk about type inference. And here's the observation. What's the type of interp0? Var to nat. And so we clearly mean to evaluate x under an interpretation of type var to nat. So we know that we're going to get a result of type nat. Lean should be able to figure out that this is going to return a value of type nat. So alpha has to be nat here. Just given x and the interpretation, in fact, just given this value here, interp0, you know that this alpha has to be nat. And so you know that this type has to be var to nat. So why should you have to specify nat explicitly here when Lean could figure it out, given the remaining arguments to this function eval? And the answer, of course, is that Lean gives you a nice way to avoid having to type out on your keyboard and in your code these type arguments when Lean can figure them out anyway. In fact, let's copy and paste this code to here, and I want to show you what I mean. You've seen that I've used underscore a couple of times to represent a kind of a placeholder in Lean, and that's a different use than in pattern matching, by the way. Now, if I put an underscore here, in all previous cases, you've seen the underscore with a little red squiggly underneath it, and Lean says, I can't figure out what value goes here. But if we put an underscore in this position now, there's no red underline, because Lean can figure out what goes here. Okay, so we actually don't have to type those type names here at all, because Lean can figure out what those argument values are. Lean looks at this overall function application. It looks at the types of the arguments. It says to itself, interp0 is a function from from var to nat, the function applies a function of type var to nat to a value of type var. It must return a value of type nat. So the only thing that this can be is nat, and lean actually plugs in the value nat for you here. Okay. Similarly, it figures out that this has to be the value bool in order for the rest of the expression to work. There's just no other possibility. Okay, so you can avoid some typing, but it gets better. If you want not to have to represent, if you want not to have to type those underscores at all, there's a nice way to do this. So I'm going to define a slightly different function, eval, with a different name, with a tick mark on it. And the only thing that I'm going to do here is I'm going to enclose this type argument in curly braces rather than in parentheses. Okay, and now I can evaluate eval tick mark expressions. So I'll put a tick mark here instead, and I get some type errors because lean does not expect me to provide that type argument at all. So now I can just leave out those type arguments and don't need to provide them at all. So let's actually name our first function eval prime, and because we're going to replace it with this nicer eval function like that. Okay, and here you go. This is very cool. We define a polymorphic function eval that takes a type parameter alpha and that accepts that parameter implicitly. You don't need to give the alpha value explicitly right here. Lean figures it out for you and tells you not to provide it explicitly. It doesn't want you to provide that type parameter at all, even with an underscore. Okay, and so now we have these beautiful expressions here, and let's look at them and sort of, just be amazed at what we can now do. We've written an evaluation function, eval, that takes an expression in our language, in this case an x or a y or a z or a w, and that takes an interpretation function from expressions to some domain, and that returns the value of that expression, x, in that domain under that interpretation function. Here the interpretation function is from objects of type var to nats. Here the evaluation function is from values of type var to bools. And the same polymorphic evaluation function works in either case. Okay, so in this lesson, you've seen how to define the syntax and the semantics and asemantics of a little language. Here it's just a little language with just 4 variable expressions in it, and that's all. Okay, they look like variable expressions. That's all. You define the semantics by defining interpretation functions, and you define an evaluation function that takes any expression in the syntax of the language and returns its corresponding meaning by applying a given evaluation function to that term. Okay, this is a lot. The example is very simple. It's so simple that you're intended to be able to completely wrap your head around it with an hour or two's worth of study and effort. Okay, it's really, really, really important that you really understand what's going on here. And of course, everything works, so you can, type this in on your own. You can do experimentation. You can add eval and check statements. Spend some time really, really working with this code to make sure that you understand all of the elements. And of course, I'm here to provide help anyway. So let me know if you need any help. We'll get you additional help here shortly because now's the time where things really get going in earnest. And again, part of your upcoming assignment, which is going to be due in just a few days, will be to go through this lecture, type all of this stuff in on your own. So at the end of the day, you should have what you see on my screen here, and then to fill in answers to a few additional exercises that I'll be providing here to you shortly. Okay? Good job, everybody, and see you again very soon.